Okay, good afternoon, everyone. Let's get started. So again, just reminder, tomorrow will be the due of our homework 0. This is a quick refresh of our basic mathematical knowledge, and also kind of like enforce you to use matrix vector derivatives. Okay. But if you need some help, please do not hesitate to go to the office hours. Okay, so let us continue with the basic knowledge review. At the end of last lecture, we talked about definition of the convex functions, right? So so there's a pretty tedious definition, which talks about inequality, right? So basically, if you pick up any 2 points in your domain, and for any ratio which is between 0 and 1, if you can ensure that when you function evaluated at this combination of x1 and x2 in terms of t, this function, when it is evaluated at the combination of x1 and x2, right? It must be less than or equal to the combination of function values evaluated at x1 and x2 accordingly. This is called convex function. Okay. So, sorry, please bear with me. I got some cough recently. So it's not very easy to memorize this equation, but it's always intuitive to look at the figure, right? So just keep in mind, the convex function is always like shape, something like this. So you can view like there's some kind of arc, like downward. It's like downward. That's typical shape of convex functions. So we talk about how to check if a given function is convex or not, right? So the first sufficient condition is that, okay, if for any x, y, you can show that this inequality holds, fx is no less than fy plus the gradient of function evaluated y dot product with x minus y. Okay. So we discussed in the last lecture that the right hand side here essentially is a tangent line, right? If you could remember, right? This is a typical definition of tangent line, right? So fy is the intercept, right? When x equals to y, then function value is f of y, right? And the gradient of f at y is actually a slope. Okay, it's a slope of the tangent line, okay, at the position y. Okay? So if you take a look at y here, right? So this one, if you draw a tangent line at the position y, that means at y, oops. Wait a minute. There's still some. really annoying. Let me share. All right. Okay. Sorry. So I guess there's some kind of loose contact about this line connecting iPad and my laptop. Okay. If we draw a tangent line at y here, so the slope will be just a gradient of f at y, right? And you know that this line must pass through y and f of y, right? If you just check this, this is correct. Does it make sense? Any question? I'm just repeating what we have discussed in the at the end of last lecture. Okay, so this inequality just tells us that if you're dealing with a convex function, then every tangent line of that function stay below the whole convex function body. Okay, if you draw tangent line here, you draw tangent line here, you draw tangent line here, like they're tangent to the convex function at different positions, but all the tangent lines are below the entire function body. And second commonly used sufficient condition is that if your function is twice differentiable and its Hessian matrix is semi-positive definite, then it must be a convex function. So now let us look at a very well-known inequality associated with convex function. So if a function is convex and you have a random variable x, then you take expectation of x, then you evaluate function at the expectation of x is less than or equal to, you take expectation of f of x. And this one can be further extended in a little bit more complex form. Right? So if you redefine another random variable, which is function of x, like g of x, right? You apply the preliminary Jensen inequality again, you immediately get this, right? So there's some kind of trick. If you can observe that, okay, there's some composite function where the outer level f is essentially is convex and the input is always it's just some transformation of x, then you can use this trick to show some inequalities. Right? Mm-hmm.
It has both the conditions. One is quite meaning it is quite differential.
Yeah. That's a precondition. Like if you want to apply this, you need to ensure that your f, f is at least so the first equation is differentiable, right? The second one must be twice differentiable. Otherwise, you cannot check the Hessian the inequality.
So just every time you test convince you get the test.
This is just the two commonly used ways to test convexity. If your function f is not differentiable, and of course, these two sufficient conditions are not available, right? Because you cannot apply gradient. And then probably you're gonna return back to the definition. Or there are some other rules like composite form of convexity. I give a function is a composite function of the convex functions, and this function itself is monotonic, and then there's some kind of results. There are a bunch of such kind of conditions which we do not list all of them because it's not convex optimization problem, convex optimization class. But if you're interested, you can find any convex optimization block, at least a lot of problems. Other question? Okay, thanks for the great question. Okay, this is Jensen's equality. So now, well, we're gonna talk about one last important thing about convex functions called convex conjugate. So you might have seen it in our homework problems, right? And here we're gonna give a more formal introduction of convex conjugate. Sometimes it's called French duality. So if as long as we have some convex function f, so we can represent f in terms of another form, which we call its conjugate. So that means for any convex function f, we got another function lambda, which we call f and g are convex conjugates. So what kind of relationship between f and its conjugate? Okay. We can represent f as maximum of a linear term lambda times x subtracted by the conjugate g of lambda. In other words, suppose g of lambda is given, right? So given any x, okay, if you want to know the value of f of x, you can instead solve this maximization problem in terms of lambda. And shows that the maximum of this right-hand side with respect to lambda is f of fx. Is the definition clear? And symmetrically, if you look at the conjugate itself, like how can the conjugate be represented in terms of f of x? Right? The conjugate function's value at any lambda can also be obtained by solving another maximization problem. Right? This maximization problem is again the same linear term lambda x subtracted by f x. And this time I'm gonna given lambda, right? Lambda is fixed. I'm gonna solve this lambda x minus fx with respect to x. Then the maximum value of this guy with respect to x will be g of lambda exactly. Is it clear to everyone like how this is described? I'm gonna explain some intuition later, but I need to ensure that everyone gets the definition of this. It's fine. X is vector, then this one is lambda will be a vector, and this term will be lambda transpose x. Another question? Okay, that sounds good. So but in case that if you still feel a little bit uncomfortable, you can view like right-hand side as a function of y variables. right? You can view it as a function of x and lambda, right? And for the first line, right? When we want to get f of x at any x, right? That means you're gonna fix x, you're gonna maximize h only with respect to lambda. And it tells you that, okay, the maximum value with respect to lambda will be f of x. And similarly, about conjugate g of lambda, right? You can view this one as another function, say beta x lambda. So if you want to get the value at any specific lambda, right, you're gonna fix lambda here, maximize this beta function with respect to x only. And then it gives the result that maximum beta will be the value of g of lambda. Does it make sense? Okay, so now this is a conclusion and this is theory. We don't need to know, we don't need to like rigorously prove that. I just want to give you some intuition how they kind of get this, and how they arrive at this beautiful conjugate pairs. Right? Sorry. Okay. Let's start with this one, right? So I want to give you a conclusion. Now, this one essentially is the tangent line, which connects to what we have just discussed, right? So the right-hand side is just the tangent line at x, tangent line with respect to x. Right? So y for any particular x, we will have to change the slope of tangent lines, and we're gonna find out one particular tangent line such that when you evaluate x, the tangent line's value, y output of the tangent line's value is the same as the function, convex function. How can we see that? So let me draw a convex function. So as we just mentioned, right? So if you view the right-hand side, like given lambda, you vary the x, and this is essentially a tangent line. Tangent line means that, okay, you're gonna be tangent at any particular point. At a particular point of this convex functions, please bear with me. Okay. So you see that this could be lambda 1, this could be lambda 2, this could be lambda 3, and so on, right? So you can see that when you vary the slope of the tangent line, actually at which position you're going to touch the function f will change as well, right? So let us pick up a particular point, x, right? So suppose this is my x. So if you evaluate the tangent line, all kinds of tangent lines, right? Here, here, at the same position x. Here, what can you observe? So we know that this is where it's f of x, right? And if you evaluate, if you look at the function value of tangent lines at x, what can you observe? Yeah, 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 yeah. That's a good observation. Right. So basically, what David said is, you can see that actually all the tangent line when they evaluate at x, they're below f of x, right? So you can see for lambda one, right? For lambda one here is here. When you look at this tangent line, when they evaluate x, this is where the value, right? And for lambda two is here. If you just stand there, right? You evaluate x is here. It's even smaller, right? As compared with f of x, right? For lambda three, let me use another color. Lambda three, like something like this, right? To evaluate x, the value of this tangent line function is also smaller than x, right? So now I want to ask, do we, or is it possible for us to find out the tangent line when they evaluate x, it is exactly the same as f of x? Any thought? Yeah. Remember, you can take you can change the slope at any position, right? So what if I just draw a tangent line which right pass through x, right, and f of x? I mean, it's the point which this tangent line touch the convex function is at x. Then we know that, okay, when I evaluate my tangent line here at x, it will overlap with the function f, right? Does it make sense? Like if you change the other slope, right? If it's not this here, you just change the slope. You can increase it or decrease it. You see that it's gonna always like you can have a let me use let me draw this convex function more clearly, right? So we change the slope. That means you change the point at which you're gonna touch with the function body, okay? And then at x, specific position x, you can always be below f of x, right? Only when you choose to touch your convex function f right at x, then your evaluation at x will overlap with f of x. Does it make sense? Okay. So that's why f of x is arrived at, you take the maximum value, you take some slope of lambda, which is make your tangent line value at x maximum, right? Because all the other tangent lines at x, they're smaller, right? You kind of like adjust lambda. Look at the right hand side, you're adjusting lambda such that you find out lambda whose tangent function value at x is the maximum, right? That's the meaning of this. Does it make sense? Any question? Just let me know. Don't be shy. Just let me know if you feel anything uncomfortable.
So you're saying that every other tangent line.
Yes. 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 That's it. That's why this is the maximum, right? Because for any other cases, for any other choice of lambda, your tangent line value at x will be smaller than f of x, right? So that's why it can be written as a maximum of this tangent line values at x. And it also tells us as, okay, what kind of lambda will give you this maximum? It will be the slope of the tangent line, which pass through x and f of x. Right? Any question? Okay, that's fine. If you feel still uncomfortable, I mean, this is a little bit it might take a few more minutes to get it, but I will suggest you after the class you can like draw lines like me. You can draw much better lines than me, and you'll get it. Okay, so now we just mentioned, right? This guy, I just state that, okay, this guy is a tangent line, right? But why is so? Why should I claim lambda x subtracted by g of lambda will be a tangent line? Okay? I'll explain it with the second definition. That is, g of lambda is written as maximum of lambda x subtracted by f of x with respect to x. Okay? You will see that actually doing this optimization will give you the intercept when you use lambda as the slope to construct your tangent. So remember, if I draw a tangent line, right, I can choose arbitrary slope to construct a tangent line of this f of x, right? Then the problem is that, okay, I know the slope, but I don't know the intercept. Right? You cannot be arbitrary intercept because this tangent line must at least touch one point of this function body, right? So this one just tell you how you're gonna get this intercept. Okay, so as we just mentioned, right, this one is a tangent line. That means the intercept is negative g of lambda, right? So in other words, I mean, for easier understanding, right? If we want to get this intercept, like this guy is called intercept. Okay. If you want to verify this intercept is indeed the intercept that you use slope lambda to construct the tangent line. Right? Let's look at whether it is so, right? So according to here, right, g of lambda is maximum of this guy. That means minus g of lambda is minimum x and f of x subtracted by lambda x. Right? So we're gonna verify that, okay, by doing this minimization, indeed, it gives you the intercept of your tangent line with slope lambda. Okay. Are we on the same page? Okay. Yeah, okay, let me repeat again. So okay, so this is suppose this is your convex function, right? As I said, right? You can choose arbitrary lambda to construct your slope. Right? For example, if you choose the slope lambda 1 here, right? Then your intercept will be here, right? And if you choose a different lambda, like lambda 2, right? Like lambda 2. Like lambda 2. You have a different intercept, right? So actually your intercept kind of vary with lambda, the slope. Right? Does it make sense? Right? You can try a third one, right? Like if you choose a third slope is in this way, right? Like you have a third intercept, right? So you know the intercept, right? You know the definition of intercept. Right? If your function, linear function a equals ax plus b, then b is the intercept. Right? That's basically how far away from the origin, right? So what I'm claiming is that, okay, this negative g of lambda is exactly the intercept when you choose your lambda as the slope of your tangent line. What is the intercept? Does it make sense? Right. This is something I want to show. I'm planning to show you in a minute. I run clear on my intent, right? I intend to show that, okay, this negative g of lambda solved by minimizing this procedure actually will give you exactly the intercept of the tangent line with the slope twice lambda. Right. How could we say so? Right? How could we say this point? So according to this definition, minus g of lambda is minimum fx subtracted by lambda x, right? With respect to x. Right? So let us try to, because this is too messy, so let me redraw it. Okay, this is my f of x, right? Suppose I choose a lambda is like this. This is my lambda x, right? If I write it as if I draw it is actually a line which passes through the origin, right? So now let us look at how do we optimize the difference between f of x and the lambda x. So for at any x, we know that the difference will be just see at here, like you just look at difference here. This is a line segment which is vertical, right? And you can see you vary x. You have different fx subtracted by lambda x. Does it make sense? Right. So now I want to ask, for my particular choice of slope lambda, right? At which x will we get this difference to be the smallest? In other words, at which place we'll make those vertical segment to be the shortest? How can we find out this position of optimal x? Just use our high school geometry stuff. No need to provide. Yeah, you get a point. You get a point. But let us do it more formal, right? The bottom. What do you mean by bottom? I guess you're saying like it's not horizontal, it's not it should be vertically, right? Mhm. You take derivative set to 0, take a derivative of which. Yeah, but what's the objective one? Oh yeah, of course you can take derivative set to 0. That's how we get g of lambda. I just want to give you like intuition, like geometrically, how do you find out this act? Okay. So I want to know, okay, we know that this vertical segment, right? This blue vertical segment indicates at every possible x, the difference between f of x and lambda x, right? So if I want to find out a particular segment which is shortest, the easiest way of doing this, or most intuitive way of doing this is that, okay, I'm gonna just sorry, move this lambda x, right, parallelly upward, right? I just slowly move it until I first touch the function body, right? So if you touch second, that means you're gonna pass 2 points, right? But if you touch the first, you actually have being tangential to the function body, right? So just move this lambda x upward until you, for the first time, touch the function body, right? So at this place, this is essentially correspond to a tangent line of f of x, right? And then you can see at the touch point, suppose here, this line segment is smaller, is shorter than any other line segments, right? Why? Because for any other line segment, you always have some f of x is kind of going upward, and this guy is still flat, right? There's always some difference here. So you can see that all these green segments have the same length, right? Because you're moving at lambda x, this line, in parallel, like upward, right? But the true difference is you need additional true difference. You need additional difference, right, to account for the whole difference between f of x and lambda x. Okay. That's why for other places, this f of x subtracted by lambda x is bigger than here. Does it make sense? Okay. And then at this point, let me denote this by x star, right? Your fx star subtracted by lambda x star is the minimum, right? So now you tell me, what's this minimum value represent? As we just mentioned, right? We find out when you find out this optimal x star, right? You actually has got a tangent line, right? And this position or this difference, you can move it in parallel, right? Here, it's the same, right? So this actually is the intercept, okay, of the tangent line here. And this tangent line has a slope exactly lambda. Does it make sense? Okay. That's why we claim that, okay, when you solve this minimization problem, you get minus g of lambda. This minus g of lambda is exactly the intercept when you use lambda as your slope of tangent line. Okay. Any question? We're on the same page, right? Like if you feel like still feel uncomfortable, it doesn't matter. I mean, you just follow what I did. Draw this line and think about the meaning, and you will get it like in 5 minutes. So it doesn't matter like if you still feel uncomfortable about those things, it's okay. I just want to give you some intuition here. Okay? You might need a few more minutes to digest, but it won't be very hard. Yeah. So why do we introduce this so-called convex conjugate? Because the Jensen inequality and convex conjugate will play the key role in the approximate inference. Okay? And of course, when we are talk about the approximate inference, we won't try to draw this line again and to explain what is geometry meaning for that is not necessary. All you do at that time, you just try to maximize this, say take the derivative and set derivative to be 0 and then get the form. I just want to give you some geometric meaning for that to strengthen your idea about this. Okay, so now we're going to proceed to basic concepts regarding probability. Okay? So the previous discussion mainly about convex and matrix vector machines, matrix vector derivatives, all those kind of stuff seems not directly related to probability stuffs. So now we're going to talk about, or we're going to review the basic concepts in probability. So, so we're going to briefly introduce what is probability space, okay? So to give you a more formal definition about probability. So basically, when we talk about a probabilistic model, so, you need to assume that you have some probability space in your mind, right? So what is probability space? It is a mathematical structure which is a triplet. Like you really assume that you're gonna have a sample space. You're gonna have a event space. You're gonna have a probability measure. Okay. So sample space usually means those atomic experiment outcome. Like for example, if you are interested in modeling the rate of your gambling, right? If you're rolling a die, right? Then the basic unit of the outcome is just the point, right? Just the point when you roll a die, like 1, 2, 3, 4, 5. So you have just one die, and that means you have 6 points, right? So your sample space might just contain like 6 outcomes, 1 to 6, right? And then the even space means that the possible combination of the elements in the sample space. Like, for example, I want to talk about the probability that my point is bigger than 3, right? So that actually corresponds to a subset of the sample space outcome, sample space elements, which is 3, 4, 4, and 5, and 6, right? So actually, even space you can view as all possible valid events constructed based upon the elements in the sample space. And then the probability measure just tells you what kind of probability I'm going to assign each possible event in my event space. That's the general definition, right? So now let us look at the definition of each item here, like one by one. So first, what is sample space, right? A sample space is a set which contains all possible outcomes of a random experiment, right? If we talk about the discrete outcomes, like if you toss a coin, right? If you want to look at all kind of uncertainty or randomness, will toss a coin, then the basic unit of your outcome will be just heads up or tails up, right? So then your sample space consists of two elements, H and T, right? Heads and tails, right? When you roll a die, then your basic outcomes is the point. Right? Is 6 points, is 1 to 6, right? Sometimes you want to look at the radiation of some materials, right? Then we want to look at the radioactive decay. Then we want to look at the number of particles emitted per minute, right? And then your basic unit of the outcome will be just non-negative integers, 0, 1, 2, 3, 4, 5, 6. And in theory, it could be as large as possible, right? And continuous examples, right? For example, height. It could be any continuous non-negative number, right? Or image pixel value, right? Image pixel value. There's like upper bound, so it's a range between 0 and M. So this is called sample space, right? So what is an event? Event is a set of elements in the sample space. So suppose this is your sample space. That means it contains all possible outcomes of your random experiments. An event just means you pick up a set of them to form a event. For example, you're rolling a die, right? Now, I'm going to construct an event that an even number is rolled. Okay. This is a valid event, right? So this event essentially can be represented by a set which consists of a 2, 4, 6, right? Because it tells you that you only see an even number, right? So it is possible to be 2, could possibly be 4, possible to be 6. And if you look at the spruce tree, right? Spruce tree, if you consider the event is that you saw some tree which is taller than 80 feet, okay, then this event can be represented by this range between 80 to infinity, right? Because this means that the tree height is no less than 80. Okay? It's bigger than 80. Okay? But all possible tree heights will be infinite, right? Will be 0 to infinity. Right? Any question? Is everyone comfortable with this? I think this is just a generalization of like basic definition of probability everyone has seen before. Right? We use a set of basic outcomes to represent different types of events, right? And then we believe that we can use the set operations to create new events, right? For example, two events represented by set A and set B. If I union them, I got a third event. If I do an intersection of them, I got a third event. If I do a completion, if I do a subtraction, I got new events, right? So you can imagine that I can create some fundamental events, right? Maybe several, maybe just a few subsets of the elements in the sample space. And then I can construct composition of the union, intersection, completion, and subtraction, so that I can construct a lot of all kinds of events and complex events, right? Then that leads to a question, right? So what possible set of events should we choose? You can define all possible events which you're interested in, right? So all possible sets of events, all possible events, which is another set, is called event space. So now I want to ask a question, right? Can I pick up arbitrary a collection of events and define it as my event space? Like suppose going back to here, right? So we know that this is a sample space, right? And I pick up a subset of elements in the sample space. I create one event, right? And I pick up another subset of elements. I create another event, right? And can I just create up whatever arbitrary a collection of events, and then I say, okay, this is my event space. Do I have such freedom? Just give me a guess. You can have like you can pick up any collection of events which are just subsets of sample space. Okay. Any other thought? Mm-hmm. Uh-huh. Mm-hmm. Yeah, you can overlap. Of course, you can overlap. Like if they're identical, then that actually represents the same event, right? As long as they're not identical, it's totally fine. Yeah, my question is that okay, since it's kind of like very flexible to construct an event, right? You just pick up arbitrary set of sample outcomes, right? So can we just pick up any collection of events and then just focus them and to do everything I want? Don't worry. This is just ask you to guess that. It's not ask you to prove anything. Okay, but let me give you an answer. No, you cannot do that. The reason is simple. If you are allowed to pick up any collection of events and then to construct your event space, then you assign a probability measure on that, and you do all kinds of probability inference calculation that will lead to paradox. That will make you inconsistent. This is a very, very famous paradox. Okay. So if you want to construct a consistent and well-defined, not ill-posed event space, your choice of collection of events must satisfy some basic properties. And usually a valid choice of a collection of events form a so-called sigma algebra. Don't ask me why this is called sigma algebra, but this is defined. They call it sigma algebra. Okay. So, so what does sigma algebra satisfy? So first, in your collection of events which form your event space, you must contain the empty event. Maybe an empty set must be belong to F. And second, your F must be closed under countable unions of any events in your F. So basically it says, okay, for any set of and for any collection of events in your F, right? Then you do the union of them, it still belong to F. It cannot be outside. And here, just to give you a sense, this is called countable union. That means your number of events can be infinite, right? But they can be indexed by integers like a1, a2, a3, a4, a5 until a infinity. Right? It just tell you, okay, if you union them all together, it will still belong to F. And third one is called completion. Right? So if A, there's even A in your F, then the completion of A must be in F as well. Right? Only when you construct your even space following this three properties, and you can have the nice property, you don't need to worry about any contradiction and paradox. Okay? And this is called sigma algebra. To just give you a sense, you won't need to prove anything with sigma algebra. You won't need to compute anything that you have to consider sigma algebra, but it's just conceptual definition. Okay. Any questions so far? Okay, once we have a valid sample space, we have a valid even space, right? Then we talk about, okay, the events. Here's your even space F, right? Any point in your even space is an event, right? And then we need to consider, okay, how we're gonna assign the probability over each event. Right? What's the chance that each event in my even space to happen? Okay. That means you need a third component in your probability space, which is called a measure, right? Probability measure. So let's first talk about measure, right? So what is measure? Measure is a function, right? It's a mapping between a sigma algebra to a non-negative number. So remember, sigma algebra actually is a set, right? It's a set, right? And each set consists of another set, right? So sigma algebra is a set of sets, right? And this measure must satisfy the following properties. First, the measure on an empty set must be 0. And second, if you have a arbitrary collection of the events or elements in your F, right? If this A1, A2, A3, all kinds of stuff like pairwise disjoint, they do not overlap, right? Then your measure over the union of those sets A1 to A infinity must be summation of their measure over each individual set. So this actually gives you a rigorous definition about like how do you compute a volume, how do you compute an area, right? So in a mathematical space, like in practical applications, like if you look at this table, you want to look at, okay, what's the area of this table? You actually don't have, you have some like intuition, right? Looks like the space, the more space they occupy, the larger the area, right? But if you look at the abstractive level, right? If I want to use math to rigorously define what is the area, how can I do that? Right. So in a mathematical space, everything is defined as a set, right? So your table is a set of points, right? Your desk is a set of points, right? So the area essentially is to map this set of points to some positive number, right? So I think this area, the area of this is like 1 square meters and 1 square feet. And in the mathematical space, I'm gonna assign a positive number as the measure of this set. Okay. And of course, this measurement can correspond to area, can correspond to volume, it correspond to any other things you feel is measurable. Right? So intuitively, you believe that okay, a good measurement must satisfy the following properties. First, if your set is empty, that means it doesn't contain anything, then your measure must be 0, right? And if you're if the set that you want to measure can be partitioned onto disjoint subsets, right? Then the measure over the whole set must be the summation of measure of each individual set, right? That's actually why this is defined like this. Right? Does it sound good? Does it sound reasonable? Okay, then if we put constraint or put restriction on the measure function, if you define your measure over the whole set is simply 1, then this measure is called a probability measure. So remember, this is sample space, right? So I actually want to say, okay, the measure over the whole sample space is simply 1. Sorry. Then any subset of the sample outcomes which correspond to some event, the measure will be less than or equal to 1, right? So that's reasonably can be explained as a probability or a chance. Any question? So now we come to our definition of probability space. So probability space is a triple. Okay? It contains a sample space, which is a set. Okay? Each element in the sample space a basic outcome of your random observation. Okay? And you have even space F. F is a sigma algebra. Is actually a set of sets. Right? Each set in F is a subset of omega. Okay? And each set in F represents an event of your interest. Don't have a valid even set as your even space, then it might those properties, and it's called sigma algebra. Right? And third, you got a probability measure P defined on sample space and even space. Right? The probability measure ensure that the probability over the whole set, whole sample space is 1. Right? Okay, so far any question? Is everyone on the same page? We're on the same page, right? Okay. Makes sense, right? We're not going to like very deep about those definitions and also ask you to show anything. But I just want to give you some structure. Right? We will seriously talk about the probability modeling. You should have some structure probability measure in your mind. Okay. So now that sorry, please forgive my throat. So so there are some properties of our probability measures which we have seen them for a long time, right? So if you have an event A, then the probability of the completion A is 1 subtracted by P of A. Okay? So people use this as by default. Actually, this could be some assignment problems for you to show in some like measurement measure theory class. You have to show this, but right now people right now, let us just assume this it's kind of an axiom you can use by default, right? And the probability measure over the union of two events A and B is equal to P of A plus P of B subtracted by P of A intersection with B. Right? So, so this one is very intuitively can be explained by this Venn diagram, right? So this is A, and this is B, and the probability of A union with B is actually the area of A union of B, right? So it can be computed by you add the area of A and also add the area of B and then subtract it by the place, the area you like count twice, right? And based on the probability definition, we can also define the conditional probability, right? So the conditional probability of even A given even B is defined as follows, right? So it's defined as the probability of A intersection with B divided by probability of B. So this one is called joint probability. Sometimes it is written as PAB. So here's one example. I'm not gonna go through this because I believe everyone is familiar with this, right? It's joint probability divided by the marginal probability. This is called conditional probability, right? And independence, right? If we got two events A and B in the sample space, we say A and B are independent if their joint probability can be written as the product of the marginal probabilities, right? PA union intersection with B equals to P of A times P of B. Then we call A and B are independent to each other. Right? If two events are not independent, they are called dependent, right? So if this inequality doesn't hold, and then you say A and B are dependent. So we can define independence in another way, right? So if the conditional probability of A given B is just the marginal probability of A. So intuitively it says, okay, given B or not given B actually doesn't affect my chance that A happens or not. Okay, so A and B are independent. Okay. But this can also be easily shown from the original definition. Okay. So similarly, if the conditional probability of B given A is exactly the same as the marginal probability of B, then A and B are independent. So these are just put them together, right? So these three conditions are equivalent. P of A given B equals to P of A, P of B given A equals to P of B, or P of A intersection with B is P of A times P of B. They're equivalent, and they all say that A and B are independent events. Okay, so now let us introduce random variables. So when we talk about random variable, in most of the cases, like we're assuming that okay, X might be some number, right, or some vector. It has some randomness. That's our by default how we think of a random variable X, right? But the fundamental definition, or if you look at the low level detail, random variable actually is a function. It's not random. It's also not a variable. It's a function. So what is the definition of random variable? A random variable is a function defined on a probability space, right? So if you have a probability space, which is triplet omega f and the probability measure p. Then a random variable is a function x, which maps the sample in the sample space to some set V. This is the most general definition, right? But in most commonly used case, V will be chosen as a real domain, okay? Real value domain or real vector domain. But in general, V can be any other set. Right? If you choose V to be integer values, right? Then your random variable is actually a discrete random variable. Right? If you choose V to be R, then it is real value random variable. Okay? If you choose your V to be R to a vector of R, vector of real numbers, then is a random vector. Okay? So in some literature, you will see, okay, I got a random variable in this form. Right? So it just tell you, okay, this omega, small omega, comes from the sample space. Right? Any element in the sample space, right? The map from omega to some real value is the random variable's value. Right? So it's the intuition or the motivation is like, okay, because the probability space is defined on sets. You got some basic set of elements as your sample space, and sets of sets represents the events, right? If you want to calculate the complex composition of the probabilities, that's very inconvenient. So people think of like, why not we just map those events to numbers or collection of numbers, because people are most familiar with numbers, right? And then you can compute and you can derive, you can quantify anything much more convenient. That's the motivation why people define random variables. Any question so far? So now let us look at some example, right? So suppose you are rolling two dice, right? You're rolling two dice, right? And that means your sample space will be consists of pair of like A and B, right? A coming from 1, 2 to 6, right? B come from the same set. Right? That's our sample space, right? So we can define random variable which map any sample, right, to be the summation of this two points, right? Say if you got a sample of the two dice, the points are 1 and 2, right? My random variable defines as a summation of these 2 points, which is just simply 3, right? So if you got a sample which is 4, 4, in that, okay, your two dice points are 4 and 4, then my random variable will map it to be a value 8, right? For 6 and 5, well, map it to be 11. Right? You can define whatever function or mapping as your random variable, but you have to satisfy some constraint, like your function must be measurable. I'm not going to talk about what is measurable, but basically it tells you that, okay, you need to ensure that any inverse mapping of your random variable will map back to some event in the event space of your probability space. And otherwise, it doesn't make any sense, right? So suppose this is your sample space, and you map every sample in your sample space to some real number, for example. This is how you define a random variable, right? This might be 1, this might be 2, maybe 3.3, all those kind of stuff, right? And at the same time, your image domain or the output domain of your random variable, right? They are associated with some sigma algebra, right? If it is if your output domain is just one, it's just a real number, is a real range, then the sigma algebra over that is called Fourier set, right? So the inverse mapping means that, okay, if you pick up any set in this sigma algebra, its inverse mapping will correspond a different set of samples in the sample space, right? It asks you, okay, this guy belongs to your even space. The reason is that because I want to represent my probability space, my events, my samples in some real domain, right? So that means, okay, for any reasonable real values combination, it should be mapped back to some event, right, in my original probability space. Otherwise, it's inconsistent, right? That's the major motivation. Any questions so far? Okay. This is another simple example. Like, if your sample space is already a real space, like each sample is a number, right? You can define your random variable as an identity function. Means your input s is output s. Right? It's totally doable. Right? So once you have this random variable x, right, it's usually in the real space. Then we can think about what's the range of this random variable value can take, right? And then what is the probability that when for different range of the random variable value. For example, when I talk about when the random variable value takes a particular point, x, right, it actually corresponds to the event that the subset of samples s in omega such that its random variable value at s is x, right? So when we talk about this range, right, suppose the random variable big X is less than some small value, some value X, right? That corresponds to another event, where in this event, it is collection of the samples that the random variable value of S is less than X. So you can see different range for big X actually correspond to a different events in the probability space. And similarly, if it is between A and B, it corresponds to another set of samples in the sample space, which correspond to an event. And then we can measure the probability over those events, which is actually the measure of those range. Right? That's where we often see, okay, what is probability that X is less than X? Actually, there's some kind of like underlying operation. It's not like you have some probability big X less than X. It actually correspond to, okay, when you talk about big X less than X, this corresponds to one set of samples in the sample space such that all the random variable values at S is less than X, right? This is an event, right? So the probability of this event is represented by P big X less than small x. Does it make sense? Okay. Just keep in mind, because most of the cases, we're gonna still assume, okay, what is probability of this? Right? But if you ask what does it mean for probability of P x less than x, small x? Actually means you're gonna measure the corresponding event. And if big X is a real valued random variable on some probability space, then we we define the cumulative distribution function of X as a probability measured on a specific range of the random variable value. That is big X less than or smaller than small x, right? Because we'll take this range, your corresponding event will decide by this small x as well. So that means the probability measurement on that event will decide on x. That's why we can view this as function of small x. Okay, let's stop here today. Right? And I'm gonna go through the probability, cumulative probability distribution and probability density function and so on in the next lecture.